Okay, so are you ready to dive into some serious quantum territory? Today, we're going to be tackling the Zeno effect.
But not the one you learned back in school, right?
Definitely not.
Hmm.
We're going way beyond the classic paradox stuff. We've got a paper here by Tim Madubis.
And he claims to have found a way to basically turbocharge the quantum Zeno
A
effect.
faster Zeno effect. I'm not even sure what that means. Our listener sent this paper in, so they must be familiar with it.
Right, they probably already know how observing a quantum system can kind of freeze it in place. It's weird.
Super weird. And for the longest time, I thought there was like a speed limit to how fast you could freeze a system like that.
Yeah, and Mubis is saying we might be able to crank things up, way up.
Okay, now we're talking. But before we get ahead of ourselves, how about a quick Zeno Effect 101? Just a little refresher.
Okay, so picture a quantum system, like an atom flipping its spin and it's constantly evolving. The Zeno effect says that if we keep measuring it super, super fast, like we're asking, have you flipped yet? Every nanosecond, we can basically trap it. It can't flip.
Interesting. So it's like checking if your coffee's cooled down every millisecond, and because of that, it never actually reaches room temperature.
Exactly. It's counterintuitive, but that's how it works. Of course, Mobus takes this way further. He gets deep into the math, starting with the errors that naturally occur in the Zeno effect.
So he's looking at those tiny imperfections that always pop up in experiments.
Exactly. He wants to quantify them, understand exactly how much our real-world Zeno effect differs from the ideal perfect scenario.
I can see how that's important, but how does he even begin to measure something like that?
Well, he uses this cool tool called the Chernoff lemma. It helps analyze how far off our results are from that perfect Zeno effect we want.
So it's like a measuring stick for errors.
You could say that. It gives us a way to look at those errors and say, okay, we're this much off.
Yeah.
But then he takes it a step further. He introduces a modified version of the Dunford-Segal approximation.
Okay, now you're just using big words to sound smart.
I know. But it's not as complicated as it sounds. This approximation helps analyze how quantum operations change over time. And these operations are represented by, you guessed it, mathematical operators.
Operators, so we're doing surgery on the equations now.
Sort of. Think of operators as instructions for what we want to do to our quantum system. Mubis wants to see how these instructions, when applied over and over in the Zeno effect, how they affect the system's evolution.
So if the regular Zeno effect is like pausing a video, Mobus is trying to figure out how to fast forward and rewind with perfect control.
Exactly. And the key is in how he uses those error terms we talked about. He gets this super detailed picture of what's going wrong, why it's going wrong, and most importantly, how to fix it.
Okay, now we're getting to the good stuff. This is where I'm guessing the multi-product part comes into play, right?
You're way ahead of me. Yeah, this is where it gets really interesting.
So tell me, what is Mubis' secret sauce here?
Yeah.
How do we actually make the Zeno effect faster?
All right, imagine this. Instead of just one Zeno effect, we've got several working simultaneously, each one fine-tuned to target the system a little differently.
So it's like having a team of specialists working in parallel, each one handling a different part of the problem.
That's a great way to put it. Mobis showed that if you choose the right parameters for each of these Zeno processes, you can cancel out those pesky errors we were talking about.
It's like noise-canceling headphones, but for quantum physics. That's incredible. But how do we even begin to prove that something like that would work?
It all comes down to some seriously clever math, like diving into the spectrum of the operator that represents the entire quantum operation.
Wait, hold on. Spectrum. Like the colors of the rainbow.
Not that kind of spectrum. Think of it like a mathematical fingerprint that uniquely identifies the operator. It gives us essential information about its properties, and Mobis uses that to figure out how to combine those multiple Zeno processes.
Okay, so more like a fingerprint than a rainbow.
Right.
I'm with you. But how do we actually use this fingerprint to make the Zeno effect better?
This is where it gets really cool. Mobis introduces this amazing tool, the holomorphic functional calculus.
Holomorphic functional. You know what? Never mind. I'm sure our listeners are already lost.
It's not as intimidating as it sounds, I promise. Think of it like this. We're taking the math we normally use for numbers and extending it to these abstract concepts, these operators. It's like creating a whole new type of math specifically for dealing with these quantum instructions.
So instead of adding 2 plus 2, we're adding apples and oranges and getting a meaningful result.
You could say that, except instead of fruit, we're dealing with actions on a quantum system.
Okay, I'm starting to get the picture. So Mobus uses this fancy new math to analyze those parallel Zeno processes.
Exactly. And he proves that by combining them in just the right way, you can actually achieve a much faster convergence rate for the Zeno effect. It's like the difference between dial-up and fiber optic internet. We're talking about a massive speed boost for controlling quantum states.
Yeah, this is blowing my mind. And to think, we're just getting started. But we're out of time for today.
We've laid the groundwork. Now we need to talk about what we can build on top of it.
Exactly. We'll dive into the practical applications of the supercharged Zeno effect next time.
Oh,
Until then, keep exploring. Okay, so we've got all the mathematical tools laid out in front of us. Mobus has basically given us this instruction manual to supercharge the Zeno effect.
but I know you want to know how to use it. What can we actually do with this thing?
Exactly. Our listener didn't send this paper in just so we could admire the math, Rada. There's got to be some cool applications for this.
No, absolutely. And Mubis outlines a couple of really exciting ones. The first one directly tackles a huge challenge in quantum computing, and that's environmental noise.
Noise. The bane of any experimentalist's existence. It's like trying to hear a whisper in a hurricane.
That's a great analogy. In the quantum world, all that noise, all those stray interactions, they can completely mess up the information we're trying to store and process.
Right. It's like our quantum system is this tiny boat being tossed around in a stormy sea. We need a way to keep it steady.
And that's where the bang bang method comes in. It's a way to protect our quantum information from all that noise.
Bang, bang. That sounds kind of aggressive, doesn't it? What is this, quantum warfare?
Well, the name is a bit dramatic, but it's actually based on a really elegant idea. What if, instead of trying to shield our system from the noise completely, we just interrupt the noise constantly?
Interrupt the noise with more noise. I'm not sure I follow.
Okay, so imagine this. We apply these incredibly short, incredibly strong pulses to our quantum system. Think of them like tiny hammers, constantly hitting it, but in a very specific way.
So we're basically shaking the system so much that the noise can't get a good grip.
Basically. It's like trying to write something on a piece of paper while someone's shaking your hand. If they shake it fast enough, you can still write legibly because the shaking averages out.
Okay, I kind of see where you're going with this.
Yeah.
But how does Mobus's multi-product Zeno effect fit in? I thought we were talking about freezing systems, not shaking them.
Well, remember how we said those pulses, those bangs, are like mini measurements? Each one is like a Zeno kick. And Mobus's work allows us to optimize those kicks.
So we're not just banging away randomly. We're being very specific about when and how we hit the system.
Exactly. By carefully orchestrating those bangs using the multi-product Zeno approach, we can achieve the same level of noise protection with way less effort. It's like using a scalpel instead of a machete.
Okay, that's pretty impressive. We've gone from freezing systems to precisely manipulating them at high speed.
And that's just one application. Now let's talk about something even wilder. The bosonic cat code.
Oh boy, here we go. Cat codes. What are we, hackers now?
Not quite. Remember how our quantum system is always trying to evolve? Sometimes we want to prepare it in a very specific superposition of states, what we call a cat state.
Like Schrodinger's cat, both alive and dead at the same time. Those things always give me a headache.
Yeah, they're weird, but they're also incredibly useful for quantum computing. The problem is they're notoriously difficult to work with.
What, like they have stage fright? Too much pressure for the quantum cats.
You could say that. They're extremely fragile, prone to collapsing at the slightest disturbance. But the bosonic cat code offers a way to manipulate them more reliably.
And I bet Mubus found a way to make that even better, didn't he?
Bingo. One of the key operations in this cat code is something called the X-gate. It basically rotates our quantum state, like adjusting a dial to control the cat state.
So it's a very precise operation, especially with something as delicate as a cat state.
You got it. And here's the thing. This X-gate, we can actually implement it using the Zeno effect. By choosing the right sequence of kicks, we can nudge the system into the right rotation.
So we're back to using the Zeno effect to control those quantum states.
Yeah.
But I have a feeling there's a but coming.
You know me too well. See, the traditional Zeno effect, it's just too slow for this kind of fine-tuning. We need speed and precision, and that's where, you guessed it, the multi-product Zeno effect comes in.
I knew it. Mubus to the rescue again. So tell me, how much better can we make this cat code manipulation?
It's not even a competition. Mobus's method lets us synthesize this X-gate way faster and way more precisely than ever before. It's like the difference between playing a note on a piano with your whole fist versus using one perfectly placed finger.
So we were talking about a total game changer for controlling these cat states. What kind of impact can that have?
The possibilities are huge. This level of control over cat states could lead to more robust quantum memories, more efficient algorithms, and ultimately much more powerful quantum computers.
I'm starting to see a pattern here. It seems like every time we talk about the Zeno effect, we end up talking about revolutionizing entire fields.
That's the beauty of it. It's this seemingly simple concept that has profound implications for how we interact with the quantum world.
And how we build the technologies of the future. But before we get ahead of ourselves, I want to make sure we're not glossing over the details. We keep mentioning the bang-bang method and this bosonic cat code, but how does Möbius's work actually play out in each case?
You're right, we should get into the specifics. Let's start with the bang-bang method and how we can actually implement it using this souped-up Zeno effect we've been talking about.
Okay, let's break this down. We've got our quantum system, and it's swimming in a sea of noise.
And we want to protect it, right?
Yeah.
Keep it stable so we can actually do something useful with it.
Exactly. So how does this bang-bang method actually work in practice? We're not just going to start hitting it with a metaphorical hammer, are we?
Well, not a literal hammer. The idea is to apply these really strong, really short pulses to the system, one after the other.
Like we're sending it a Morse code message. What kind of pulses are we talking about?
They're designed to be very specific to the system and the kind of noise we're dealing with. But the key is that each pulse basically flips the system back and forth really rapidly.
So we're fighting noise with more noise.
Yeah.
That sounds counterintuitive.
It seems that way, right? But think of it like this. Each pulse is like a little nudge that disrupts the environmental noise before it can really take hold.
So we're basically scrambling the noise by introducing even more chaos.
In a way, yes. But it's controlled chaos. We're choosing the timing and strength of those pulses very carefully, so they essentially average out the effect of the noise.
Okay, I think I'm starting to get it.
Yeah.
But where does Möbius's multi-product Zeno effect fit into all of this? Didn't we say those pulses are like mini measurements, those Zeno kicks?
Exactly. And what Möbius gives us is a way to optimize those kicks, to fine-tune them for maximum noise cancellation.
So we're not just applying those pulses randomly, we're being very strategic about it.
Exactly. By using the multi-product Zeno effect, we can achieve the same level of noise protection, but with fewer pulses overall.
So it's more efficient, more elegant.
But much more. And that's incredibly important when we're talking about building practical quantum computers.
Right, because every little bit of noise adds up.
Yeah.
Now, what about those cat states we were talking about? How do we use this supercharged Zeno effect to control something as delicate as a cat state?
Remember we said those cat states are like the divas of the quantum world, super sensitive to any kind of disturbance?
And those X gates, those are how we control those divas.
Exactly. The X gate is how we rotate our quantum state, how we write information into those cat states and manipulate them.
And the problem is that those gates, they need to be super precise.
Incredibly precise. Even the tiniest error can cause the whole thing to fall apart.
So how does the Zeno effect help us here? I thought it was more about freezing systems, not fine-tuning them.
Well, remember how each Zeno kick is like a tiny measurement? We can actually use those kicks to nudge the cat state into the right position, to rotate it just the right amount.
So we're essentially using a series of tiny nudges to steer this incredibly delicate quantum state.
That's a great way to put it. The problem is the traditional Zeno effect, it's just too slow for this kind of delicate work.
And that's where the multi-product Zeno effect comes in.
You know it. With Möbius's method, we can implement this X-gate much faster and with far greater precision than ever before.
So we're no longer limited by the speed of the Zeno effect. We can really get in there and manipulate these cat states with incredible finesse.
It's a whole new level of control over some of the most exotic and powerful states in quantum mechanics.
This is incredible stuff. We've gone from this seemingly simple idea, this Zeno effect, to talking about revolutionizing entire fields.
And to think, this is just the beginning. There's so much more to explore.
That's the beauty of it, right?
Yeah.
Every answer leads to more questions. Every discovery opens up new avenues of exploration.
Exactly. And that's what makes this field so exciting. There's always something new to learn, something new to discover.
Well, on that note, we'll leave our listeners to ponder the incredible possibilities unlocked by this faster Zeno effect. Until next time, keep exploring those mind-bending corners of the universe. Hey everyone, get ready for a wild ride, because today we're diving headfirst into the quantum realm. We're talking about making the already mind-bending quantum Zeno effect even more powerful, if you can believe it.
It's pretty wild stuff.
We're taking a deep dive into a paper by Tim Möbius, and it's called Multi-Product Zeno Effect, with higher order convergence rates. And let me tell you, this paper, it's not for the faint of heart. It's heavy on the math, really heavy, but don't worry, we've got just the expert to break it all down for us.
I'm happy to be here. It's always so exciting to see new research pushing the boundaries of what we thought was possible, especially in a field as mind-boggling as quantum physics.
Now, for our listeners who haven't spent their week knee-deep in quantum equations, can we start with the basics? What exactly is the Quantum Zeno Effect, and why should we even care about making it faster?
Okay, so picture this. You're watching a pot of water, just waiting for it to boil. Common sense says it should take the same amount of time whether you're staring at it or not, right?
Makes sense to me.
But the quantum world, well, it doesn't quite play by those rules. The Quantum Zeno Effect, named after that ancient Greek philosopher Zeno of Elea, tells us that constantly observing a quantum system can actually slow down or even completely freeze its evolution.
Whoa, hold on. So it's like by constantly checking the water temperature, you can somehow stop it from ever actually reaching a boil. That's wild.
It really is. It's like you said, the quantum world is full of surprises.
So how does this paper propose to make this already super weird effect even more powerful? The title mentions higher order convergence rates, which honestly sounds a bit intimidating.
It's a mouthful for sure, but it's an incredibly elegant concept. Think of it this way. When we talk about the Zeno effect, we're essentially talking about controlling the evolution of a quantum system. We're trying to steer it in a particular direction.
Okay, so we're like the captain of the ship, guiding our quantum system wherever we want it to go.
Exactly. And just like steering a real ship, the smoother and more responsive our steering is, the more precise our control becomes. That's where convergence rate comes in. It's basically a measure of how quickly and efficiently our Zeno effect locks on to each step we want the system to take.
Gotcha. So a slow convergence rate is like having a laggy steering wheel. Definitely wouldn't want that on a ship or in a quantum computer, I'm guessing.
Exactly. A slow convergence rate, it really limits the practicality of the Zeno effect for things like quantum computing, where speed and accuracy are absolutely essential. And that's the challenge that Mobus is tackling in this paper.
Okay, so how does he do it? What's the secret sauce behind this multi-product Zeno effect?
Well, instead of just using a single Zeno effect, Mobus proposes using multiple Zeno effects in parallel, all carefully designed and synchronized.
So it's like having a whole team of Zeno effects working together in concert, kind of like a quantum orchestra.
Loves, you could say that. By carefully choosing these parallel Zeno sequences, Mobus shows mathematically that you can really crank up the convergence rate of the Zeno effect.
Okay, I can already sense things are about to get seriously mathematical on us, but before we dive into the equations themselves, can you give us the big picture? Just how much faster can we make the Zeno effect with this multi-product approach?
Well, Mobus was able to prove that this method achieves a convergence rate of order 1n k plus 1. Now, I know that might sound a bit like gibberish.
Just a tad.
But basically, n is related to how often we apply these Zeno interventions, and k represents the number of parallel Zeno effects we're using. So the bigger the k, the faster that convergence rate gets.
So more parallel Zeno effects mean a faster lock-on time for our quantum system. But what does that actually allow us to do? I mean, what are the real-world implications of this speed boost? Give us the good stuff.
Now, that's where things get really interesting. Mobus focuses on two major applications in his paper: dynamical decoupling and the creation of something called bosonic cat codes.
Okay, now those sound like they're straight out of a science fiction movie. Dynamical decoupling and bosonic cat codes. Let's unpack these one at a time. What exactly is dynamical decoupling, and how does this souped-up Zeno effect fit into the picture?
All right, so imagine you've got this incredibly fragile quantum system. Maybe it's a collection of atoms all in a particular quantum state, and you want to study it, maybe even manipulate it to do something useful.
Sounds tricky.
It is. The problem is it's constantly being bombarded by all sorts of noise and interference from the environment. And all that noise, it can mess up your perfectly pristine quantum states. It's a real pain.
So it's like trying to have a private conversation in a crowded room, except with quantum information instead of words.
That's a great analogy. Dynamical decoupling is like creating a noise-canceling shield around your quantum system to protect it from all that external chaos.
So it's like we're building a fortress around our quantum information, shielding it from all the chaos of the outside world. I like it. But how does the multi-product Zeno effect actually make this shielding process better?
Well, the regular Zeno effect, it can be used for dynamical decoupling, but it takes a lot of constant effort. Remember how we talked about the convergence rate being like the responsiveness of a steering wheel?
Yeah. Definitely don't want any lag when you're trying to steer a quantum system.
Exactly. A faster convergence rate means we can correct for those environmental disturbances much more quickly and precisely. It's like we're upgrading our fortress walls from flimsy wood to reinforced steel.
No, that's what I'm talking about. So our quantum system is much safer and more stable inside that heavy-duty shield. Okay, I'm ready for the next sci-fi term. What on earth is a bosonic cat code?
Now, this is where things get really mind-bending. We're talking about encoding quantum information onto special states of light called cat states. And these cat states, they're superpositions of two completely different states of light, both existing at the same time. And they're incredibly sensitive to any kind of disturbance.
Hold on, cat states. Like Schrodinger's cat, but with lasers instead of a feline in a box.
You got it. Schrodinger would be proud. And the multi-product Zeno effect gives us a way to manipulate these incredibly sensitive states with a level of precision we could only dream of before.
Okay, my brain might be melting a little bit, but I'm hooked. So we can create these super delicate cat states, and then we can use this multi-product Zeno effect to control exactly how they evolve. But before we get too far ahead of ourselves, why are these cat states so crucial for something like quantum computing? What makes them so special?
That's a fantastic question, and it gets right to the heart of why this research is so incredibly exciting. You see, one of the biggest hurdles in building a useful quantum computer is dealing with errors. Even the tiniest disturbance can throw off our quantum calculations and lead to completely wrong answers.
So it's like trying to solve a complex math problem on a piece of paper, except the numbers keep changing every time you blink.
Exactly. It's infuriating. But here's the amazing thing about these cat states. They have this incredible ability to suppress certain types of errors, specifically something called bit flip errors. These are a major headache in quantum computing.
So they're like error-correcting codes, but for the quantum world?
Precisely. Cat states, they offer a way to make our quantum information much more resilient against those pesky errors that plague quantum computers.
That's incredible. But I have to ask, if these cat states are so incredibly sensitive, how do we even go about building and manipulating them in the first place? It seems impossibly difficult.
It's a challenge for sure, but researchers have come up with some ingenious techniques. To really understand how it works, we need to dive a little deeper into the math behind Mubis's approach. Don't worry, I promise to keep it as painless as possible.
All right, lead the way. I'm ready to brave the mathematical depths if it means unlocking the secrets of these amazing cat states. All right, lead the way. I'm ready to brave the mathematical depths if it means unlocking the secrets of these amazing cat states.
Okay, but buckle up, because we're about to dive into the world of convergence rates and operator theory.
You're not scaring me off that easily. I'm all in.
I like your spirit. So remember how we were talking about the convergence rate being like a measure of how quickly our Zeno effect can steer the quantum system in the right direction?
Right, like how fast it can correct its course and get us where we need to go.
Exactly. With the standard Zeno effect, we get a certain level of convergence, but it's like trying to steer a giant cruise ship with a tiny little rudder. It's slow and not very precise.
So we need a bigger rudder.
Right.
Or maybe a whole bunch of them all working together.
That's precisely what Mobis does. He introduces these parallel Zeno sequences, and each sequence is like having another rudder on our ship. And by carefully coordinating these rudders, we can dramatically improve the speed and precision of our steering.
That makes sense. More control means we can navigate those choppy quantum seas much more effectively. But how do we actually translate all of that into math? Where do the equations come in?
Well, remember how we said the convergence rate tells us how quickly the difference between our desired state and the actual state of the system shrinks to zero?
Right, like how quickly our ship is actually lining up with the route to our destination port.
Perfect analogy. So Mubis found a way to mathematically express that difference, that error, as a series of terms that get smaller and smaller as we increase the frequency of our Zeno interventions.
So the more often we intervene, the smaller that error becomes and the faster we reach our target state.
That's the gist of it. But there's a catch. These error terms, they also involve some rather complicated mathematical objects called operators and integrals. They can be a bit tricky to handle.
Operators, like those things physicists use to describe how physical quantities are measured in quantum mechanics. I'm sensing a headache coming on.
It's not as bad as it sounds, I promise. The beauty of Mobis's multi-product approach is that by strategically choosing our k-parallel Zeno sequences, we can essentially force these complicated error terms to cancel each other out.
So it's like we're strategically placing weights on a balance scale to achieve perfect equilibrium.
Exactly. It's a delicate balancing act, but when done right, it leads to that impressive 1nk+1 convergence rate that we mentioned earlier. The more parallel sequences we bring into play, the faster that error shrinks to zero, and the more precise our control over the quantum system becomes.
Okay, that's some seriously impressive mathematical maneuvering. But you mentioned earlier that Mobius used something called a Vandermonde matrix in his proof. Now that sounds a little intimidating, even for a math enthusiast like myself. Can you shed some light on that?
Ah, the Vandermonde matrix. It sounds scary, but it's actually a pretty cool mathematical tool. At its heart, it's just a specific way of arranging numbers that has some incredibly useful properties.
This is like a secret code that unlocks the full potential of the multi-product Zeno effect.
You could say that. Mobius uses this Vandermonde matrix to figure out exactly how to combine those k+1 parallel Zeno sequences to make all those pesky error terms disappear.
So it's like a mathematical recipe book that tells us exactly which ingredients to use and how to combine them to create this super efficient Zeno effect.
That's a great way to think about it.
Right.
It's a crucial piece of the puzzle that allows us to achieve those incredible speed boosts in convergence rate. But as cool as the math is, remember, it's all about what we can actually do with it.
Absolutely. And we've been teasing these applications like dynamical decoupling and bosonic cat codes. I'm ready to see how this multi-product approach takes these applications to the next level.
Absolutely. Let's dive back into those applications. First up, dynamical decoupling. Remember, it's about creating a safe haven for our quantum system, shielding it from all those disruptive environmental influences.
Right, like building that fortress around our precious quantum information,
Well
keeping it safe from the chaos of the outside world.
Perfect analogy. Now, with the standard Zeno effect, we're essentially trying to counteract those environmental influences by making constant measurements, trying to keep the system on track. It's a bit like trying to hold a beach ball underwater.
Yeah, that sounds exhausting. It takes continuous effort to keep that beach ball from popping up to the surface.
Exactly. But with the multi-product Zeno effect, it's not just about brute force, it's about working smarter, not harder.
Okay, so instead of just one person struggling to hold down that beach ball, we've got a whole team working together, anticipating the waves and coordinating their efforts.
You've got it. And that's the real beauty of this multi-product approach. We can create a much more stable and resilient environment for our quantum system. It's like upgrading from that flimsy beach ball to a sturdy submarine.
Now that's an upgrade I can get behind.
Yeah.
So our quantum information is much safer and more stable inside that robust shield. And this is especially important for those super sensitive bosonic cat codes, right?
Yeah.
Those things rely on those incredibly delicate cat states.
Absolutely. Remember, cat states, they're like those high-maintenance orchids that need the perfect environment to thrive. Temperature, humidity, light, everything has to be just right.
And the slightest disturbance could spell disaster.
Precisely. That's why this multi-product Zeno effect, it's such a game changer for working with these cat states, because by significantly improving our dynamical decoupling abilities, we can create a much more stable and controlled environment for these fragile states to exist and interact. It's like we're building a state-of-the-art greenhouse, carefully calibrated to provide the perfect conditions for our quantum orchids to flourish.
It's incredible. We're talking about manipulating the very fabric of reality at the quantum level. It's like something straight out of Star Trek. But if these cat states are so incredibly sensitive, how do we even go about building and manipulating them in the first place? It seems impossibly difficult.
It's definitely a challenge. One approach involves using a special kind of quantum operation to generate what's called a squeezed state of light.
A squeezed state. Okay, now you're just messing with me, right?
Laughs. I promise it's not as strange as it sounds. Imagine you have a balloon filled with air, and you squeeze it in one direction. The air inside, it's forced to bulge out in another direction, right?
Right, you're just redistributing the air, not getting rid of it.
Exactly. It's a bit like that with a squeezed state of light. We're not actually squeezing the light itself, but we're manipulating the inherent uncertainty in certain properties of the light waves. It's like we're squeezing the uncertainty in one aspect, and that forces the uncertainty in another aspect to expand.
Okay, I think I'm starting to see the analogy here.
Yeah.
And these squeezed states of light, they're crucial for creating those cat states we've been talking about.
Precisely. By very carefully manipulating these squeeze states, we can actually create those superpositions of light that define a cat state. It's like we're using our squeezed light balloon to create incredibly intricate shapes and patterns in the air.
This is just mind-blowing stuff. It really feels like we're on the verge of a whole new era of quantum technology.
Absolutely. And what's even more exciting is that this is really just the tip of the iceberg. This whole idea of combining multiple Zeno effects, it opens up a whole new universe of possibilities for controlling and manipulating the quantum world.
I can only imagine what other mind-bending discoveries await. Well, this has been an incredible deep dive. We've gone from the theoretical foundations of the Quantum Zeno Effect to the very real possibility of building more robust and powerful quantum technologies thanks to this groundbreaking research.
I completely agree. It's amazing to see how these theoretical advancements have the potential to revolutionize the way we approach quantum computing and beyond.
It's truly remarkable. And for our listeners, if your curiosity is piqued and you're ready to dive into the nitty-gritty details of this research, we'll be sure to link to the full paper by Tim Mobus in our show notes. Just be prepared. It's not for the mathematically faint of heart.
It's definitely a challenging read, but well worth the effort for those who are ready to explore the fascinating world of multi-product Zeno effects.
Absolutely. Until next time, keep those brains buzzing and never stop exploring the endless wonders of the quantum world. Hey everyone, strap yourselves in, because today we're going deep, and I mean deep, into the world of quantum physics
I'm excited.
with a paper that's not for the faint of heart. Multi-product Zeno effect with higher order convergence rates. But hey, that's why we've got our expert here, right?
Absolutely. It's a dense one, but the stuff about the quantum Zeno effect is seriously cool.
Okay, so the Zeno effect, for those who did really get on it, you can actually slow down how it changes.
Yeah, like if you stare at a pot of water, it'll never boil.
Exactly. Now, this paper asks, what if we could not only slow things down, but actually speed them up by messing with these observations?
And they're not just talking theory, they get into some pretty intense math. Banach spaces, holomorphic functional calculus, this is next level stuff.
Yeah, they lost me at Banach. Can you give us the layman's terms version of why that kind of math even matters here?
Basically, it's like this. Imagine trying to describe how a system changes over time, like a really complex system. These mathematical tools, they're like the language that lets us talk about those changes in the quantum world.
So it's like instead of just saying the water's getting hotter, we've got this whole new vocabulary to describe the how and why of that heating process.
Exactly. And the more precise our language, the more we can actually do with that knowledge.
Right, because in the quantum world, things don't exactly follow the same rules as our everyday experience. So where do we even start unpacking this research without, getting a PhD in theoretical physics?
Well, a key concept they focus on is the convergence rate of the Zeno effect. Imagine you're trying to cool a cup of coffee to a specific temperature. The convergence rate would be how quickly it gets there. In the quantum world, a faster rate means we can manipulate things much more efficiently.
So it's like we're trying to make the Zeno effect more practical, more useful, not just some cool theoretical thing.
Absolutely, and that's where those applications come in. One of the big ones they highlight is called dynamic. Well, they show that their multi-product Zeno effect could be used to control and manipulate those cat qubits with a level of precision that we haven't seen before. And that's a huge deal because it could change how we actually design and build those quantum computers.
So we're talking about potentially revolutionizing the future of computing. But before we get ahead of ourselves, I want to circle back to something you mentioned earlier about the math behind this research.
Yeah.
You mentioned Banach spaces and holomorphic functional calculus. Can we unpack those a bit for our more mathematically inclined listeners? They might appreciate a deeper dive into the technical side of things.
Absolutely. So Banach spaces, they're like these mathematical structures that are used to study spaces of functions with particular properties. Think of it this way. Imagine a library where each book represents a different function. A Banach space would be a specific section of that library where all the books have some special characteristic in common, like maybe they're all first editions or something. And in this paper, they're using Banach spaces to study the functions that describe how quantum systems evolve under the influence of this Zeno effect.
Okay, so they're basically organizing and analyzing those functions, trying to find patterns and insights. Now, what about the holomorphic functional calculus? That sounds even more intimidating.
It's pretty abstract, but really powerful stuff. Imagine a machine, right? And you feed it a function, and it spits out a new modified function. Holomorphic functional calculus is like that machine, but for a specific type of function, a holomorphic function, which is really well behaved from a mathematical perspective.
So it's like a superpowered function transformer. But how does that apply to the quantum Zeno effect?
Well, in this case, the researchers are using it to analyze the operators that govern how the Zeno effect actually works. It's like using that machine to fine-tune the gears inside of a watch, making it even more precise.
So they're essentially using these advanced mathematical tools to peer into the inner workings of quantum mechanics.
Exactly. And what makes this research so exciting is that it's not just theoretical. They're uncovering practical ways to harness these effects.
That's what I love about this field. It constantly blurs the line between theory and application. But I'm curious, what were some of the challenges that researchers faced in their work? I mean, we're talking about manipulating the fabric of reality here. It can't be easy.
It's definitely not a walk in the park. One of the biggest hurdles is dealing with how messy real-world quantum systems can be.
Messy. What does that even mean when we're talking about quantum physics?
Well, see, most theoretical models assume that these systems are perfectly isolated from their surroundings. Like, imagine a single atom floating in a complete vacuum.
Right. Very hypothetical.
Exactly. But in the real world, quantum systems are always interacting with their environment. It's like trying to have a conversation at a rock concert. There's so much noise, it's tough to focus.
So how do you even begin to control something as delicate as a quantum state when it's constantly bombarded by all that noise?
That's where their multi-product approach comes in. By combining multiple Zeno effects, each tailored to a specific kind of noise, they can actually cancel out those unwanted interactions. It's like having noise-canceling headphones, but for quantum systems.
Now that's clever. They're essentially silencing the universe so they can focus on the quantum music.
Exactly. It's one of the breakthroughs of this paper, allowing us to manipulate quantum systems with a level of control that we've never had before.
This is all incredibly fascinating, but we've barely scratched the surface of the math involved. Can we dig a little deeper?
Sure. One of the tools they use is a higher order error expansion.
Sounds complicated.
It can be, but essentially it's a way to make our calculations incredibly precise. See, in quantum physics, we can't always get exact solutions, so we rely on approximations. A higher order error expansion is like taking those approximations and making them ridiculously accurate.
So it's like upgrading from a blurry photo to a high-resolution image of the quantum world.
Precisely. And for something like the Zeno effect, where even the smallest errors can snowball, that precision is essential.
Makes sense. So how did they achieve this higher-order error expansion? What were some of the mathematical techniques they used?
Well, one tool was a modified Chernoff lemma, which helps analyze how probabilities behave when you repeat an experiment many times.
Okay, now you're just using big words to sound smart.
Laughs. Sorry. Basically, they're using it to figure out how likely they are to successfully manipulate a quantum state using the Zeno effect, and how that likelihood changes as they adjust their observations.
Got it. So the Chernoff lemma helps them understand the odds of success. What other mathematical tricks did they pull out?
Well, there's also the modified Dunford-Segal approximation. They use this one to handle unbounded operators, which pop up when a physical quantity like the momentum of a particle could theoretically be infinitely large.
Infinity in the quantum world. That sounds like a recipe for disaster.
It can be, but the modified Dunford-Segal approximation helps manage those infinities, making them easier to work with in calculations. It's like taming a wild stallion.
So they're bringing order to the chaos, at least mathematically. This is blowing my mind.
That's the beauty of it. But you know what? We've only just scratched the surface.
You're kidding. We haven't even touched on the holomorphic functional calculus or the spectrum of an operator, whatever those are.
Laughs. We've got to save something for next time.
All right, you win. To our listeners, stick around for part 2 because this wild ride through the Quantum Zeno Effect is just getting started.
Welcome back. Ready for round 2 with the multi-product Zeno effect.
You bet. Last time, things got pretty wild with all the quantum talk.
Yeah, we were just getting to the good stuff, though.
Exactly. So let's talk applications. This isn't all just theoretical, right?
Oh, not at all. Remember dynamical decoupling? Protecting those super fragile qubits?
Yeah, like trying to meditate in a hurricane.
That's a good one. So imagine you've got this qubit, right? And it's got to stay in a very specific state to be useful for quantum computing.
But the tiniest thing can mess it up, like a butterfly flapping its wings on the other side of the world.
Exactly. So dynamical decoupling is like we're building a noise-canceling bubble around that qubit.
Okay, so how do we actually build that bubble? What does that even look like?
Imagine you're constantly making tiny adjustments to keep the qubit stable, counteracting any disturbances.
Like a super precise quantum babysitter.
Laughs, basically. And this is where those multi-product Zeno formulas come in. Remember how they let us control quantum states faster and more efficiently?
Yeah, like our quantum babysitter just got super speed.
Exactly. So in dynamical decoupling, that speed translates to a more effective shield. We can block out a wider range of noise and keep that qubit stable for much longer.
So we've gone from a flimsy umbrella to a full-on bunker for our precious qubit.
Exactly. And the best part is they've actually shown this in their model. Combining the traditional methods with these new formulas, the results are incredible.
Music to my ears. All right, from qubit protectors to Schrodinger's cat, right? The bosonic cat code.
Oh, yes, the cat. Always a crowd pleaser. So we're talking about qubits that can be in two states at once, just like the cat being alive and dead.
It's enough to make you question reality, really.
Tell me about it. But that's the beauty of quantum. So instead of a cat, we have a cat state, which is a special quantum state exhibiting superposition.
Okay, so how do you even make one of those in the lab? Do we need a cat-shaped vacuum chamber?
What? Thankfully, no cats are harmed. We use bosonic modes, which are ways of describing the behavior of a bunch of bosons.
Bosons. Remind me, what are those again?
They're like the social butterflies of the particle world, always happy to be in the same state.
Opposite of those antisocial fermions, I'm guessing.
You got it. So a bosonic mode is like a whole bunch of those bosons all doing a synchronized dance.
Okay, I'm kind of picturing a quantum flash mob. So we use this dance to create our cat state.
Exactly. By messing with these modes, we can coax them into those weird superpositions.
Like we're choreographing a quantum ballet.
Love it. Now, where were we? Ah, yes, the multi-product Zeno effect. Remember how we need those logic gates to actually do anything useful with our cat qubits?
Yeah, like the quantum equivalent of turning a 0 into a 1.
Exactly. One of these essential gates is called the X gate. And the researchers showed that their formulas can implement this gate using cat qubits with really high fidelity.
So it's like those formulas are the musical score, and our bosons are playing the notes of the X gate.
That's a great way to put it. And this is why the bosonic cat code is so exciting. It could lead to much more robust and powerful quantum computers down the line.
Okay, now my brain is officially fried. This is all incredible, but I feel like we're just skimming the surface here, especially when it comes to the math.
Oh, absolutely. We haven't even gotten into the nitty-gritty of how multi-product Zeno effects actually work with these cat qubits. We're talking creation and annihilation operators, Hamiltonians, projection operators. It's a whole other rabbit hole.
You're killing me. All right, fine. We'll save that for next time.
Don't worry, we'll unpack it all in part 3. Stay tuned.
Welcome back to the show. We've been on a wild ride through this quantum jungle, but I feel like we're finally starting to see the trees for the forest, you know?
I know what you mean. It's a lot to process.
So let's take a second to recap. Multi-product Zeno effect. What's the big takeaway here?
For me, it's the potential. We're not just talking about observing the quantum world anymore, but actually controlling it with a level of precision we could only dream of before.
Right, like we've been handed this incredible toolkit and we're just starting to figure out how to use it.
Exactly. We talked about dynamical decoupling, making those qubits practically immune to noise.
And then there's the whole bosonic cat code, which still sounds like science fiction to me.
But that's the exciting part. These cat qubits, they could change everything about how we compute.
It's mind-blowing, really. But what blows my mind even more is that this isn't just about building faster computers, is it? It's about understanding the universe on a fundamental level.
Absolutely. We're asking those big questions like, what does it really mean to observe something in the quantum world? Are we changing it just by looking at it?
It's giving me an existential crisis, but in a good way.
Laughs. That's what we aim for. But enough philosophy for now. You promised more math.
Ah, yes, the nitty-gritty. Last time, we left off with those creation and annihilation operators, right?
Yeah.
Our quantum choreographers.
Right. So to actually build that X gate, those essential logic gates we talked about, they use a Hamiltonian.
Okay, the Hamiltonian, that's like the energy of the system, right?
You got it. It's like the conductor setting the tempo for our quantum orchestra. And they combine this Hamiltonian with a special tool called a projection operator.
Projection operator. It's ringing a bell, faintly.
It's like a filter, only letting certain parts of our quantum state through.
So some parts get a backstage pass, others are stuck in the nosebleed section.
Laughs, something like that. And by picking the right projection operator, we isolate the exact components we need to make the X gate work.
Okay, I'm following so far. Hamiltonian sets the energy, projection operator filters the state. Where does the Zeno effect come in?
This is the cool part. We apply this combination of Hamiltonian and projection operator over and over really fast. So fast that it's like we're tricking the system.
Tricking it into doing what we want.
Exactly. The rapid repetition steers the evolution of our cat state toward the desired outcome. That's the Zeno effect in action.
So we're manipulating reality itself just by cleverly poking at it really fast.
In a way, yes, and the exact timing of those pokes, that's where our multi-product Zeno formulas come in. They tell us how to fine-tune the whole process, so we get the gate we want with incredible precision.
It's like those formulas are a cheat code for the universe itself.
Maybe they are. But the implications are huge. This could be the key to building those fault-tolerant quantum computers everyone's been dreaming of.
Imagine a computer that barely ever makes errors, running calculations that would take our best supercomputers billions of years.
It's not just about speed, though. It's about tackling problems we can't even conceive of right now. Drug discovery, material science, artificial intelligence, everything changes.
It's almost too much to imagine. Well, I think we've officially blown our listeners' minds for one day.
Laughs, mission accomplished.
A huge thank you to our expert for guiding us through this incredibly complex topic. And to our listeners, as always, thank you for joining us on The Deep Dive. Keep those brains buzzing, and we'll see you next time for another deep dive into the frontiers of science. Hey there, deep diver. Ready for a deep dive into a world where watching something closely actually changes how it behaves?
It's the Quantum Zeno Effect in action, and today we're going even further with the multi-product Zeno Effect.
Okay. You're going to have to break that down for me.
It's like this, have you ever heard that saying, a watch pot never boils?
Yeah.
Imagine that, but on a quantum level.
Okay. I'm intrigued, but I think we need to take a step back here.
Yeah.
What exactly is the Quantum Zeno Effect?
So picture this. You have this quantum system. It's like a spinning coin, always fluctuating between heads and tails.
Okay, I'm visualizing it.
Now, each time you take a peek at this coin, you're forcing it to show either heads or tails. The more often you look, the less time it has to actually spin and change its state. That's the Zener effect in a nutshell.
So basically, we're kind of freezing the coin in a specific state just by observing it.
Exactly. It messes with your intuition, right? But that's quantum mechanics for you. Now, let's say instead of one person staring at this coin, we have a whole team, each with their own observation schedule. That's the multi-product Zeno effect.
Multiple observers. Isn't that going to make things even more unpredictable? How does that lead to stability?
Well, that's where Tim Mobus and his research comes in. His paper, Multi-Product Zeno Effect with Higher Order Convergence Rates, it lays out a way to actually choreograph all these measurements to increase stability.
Color me interested. Let's get into the nitty-gritty of it.
One tool Mobus uses is something called a modified Chernoff lemma.
Chernoff lemma.
Yeah, it helps analyze how errors can sneak in when you're making all these measurements to a quantum system.
Because each measurement, even the tiniest one, could nudge the system a bit off course, right?
You got it. The Chernoff lemma gives us a way to figure out how big those deviations might be.
So it's like a magnifying glass for those tiny measurement errors.
Exactly, and that's where the multi-product part comes in. By combining several Zeno sequences, each with its own rhythm, we can get those errors to cancel each other out, leading to much greater stability.
Okay, it's starting to see the elegance here. But what do these equations actually look like? How do they represent this dance between measurements and errors?
Let's take the modified Chernoff lemma as an example. What it says essentially is that the difference between naively applying a transformation many times versus applying a carefully scaled version can be expressed as an integral.
An integral. Sounds like we're about to wander into calculus territory.
This is CNEN C1, Cli-N C1, 2, CN1, CN1, TN1.
Okay, let's break this down piece by piece. We've got C, which represents some kind of transformation we're doing to our quantum system, and N tells us how many times we're doing it right.
Right. Now, on the left side, we're basically comparing two ways of doing C repeatedly. One straightforward way, and one where we adjust C each time.
And on the right side, that integral is where the turn-off magic happens.
Exactly. It tells us how far our final quantum state after those N repetitions strays from the perfect scenario, the frozen state we want from the Zeno effect. It helps us see how much those tiny nudges from measurements can add up.
So it's like measuring how much our quantum coin has wobbled.
A quantum ruler, you could say. By shrinking this integral, we make those wobbles smaller and get a much more stable system.
This is fascinating stuff, but I think my brain needs a moment to process all this.
Hmm.
Let's take a quick break and then dive deeper into the mathematical machinery behind this multi-product Zeno effect, especially that intriguing mention of higher-order convergence rates. Stick around, deep divers.
All right, deep divers, brains warmed up.
Back into the quantum soup we go. We're starting to unpack that integral with the Chernoff lemma.
Yeah, that gave us a taste of how errors can creep in with repeated measurements. But get ready, because we're bringing in another big gun, the modified Dunford-Segal approximation.
Right, that was mentioned earlier. It's all about breaking down those complex operations, right?
Precisely. We're talking about the time evolution of our quantum system, which can get really messy. The Dunford-Segal approximation lets us express it as a sum of simpler operations, easier to wrap our heads around.
So instead of tackling the whole quantum orchestra, we can focus on individual instruments.
Exactly. Here's a little taste of the math. The Dunford-Segal approximation says that for some operator C, a function of say's by the way, we can approximate its exponential, like e to the power of t times CSE, in a specific way. Ready for this?
Hit me with it.
All right, here goes. ETC0 plus TS22 CRC OCS plus S1 STC E2 CDRC E323 TSC0 plus S1 SC0 ETC0.
Right, okay, I'm not going to lie. That one looks like it could launch a rocket. Can you unpack it a bit? I see C0 and C's, which makes me think derivatives.
Yeah, to sharp eye. C's there. That's the rate of change of our operator CS. At the very beginning, SE equals 0. It's like the initial speed of our quantum system's evolution. And C's, that's the second derivative, how that rate of change itself changes. Think acceleration.
So we're essentially saying, hey, instead of this whole complicated quantum evolution, let's just figure out its initial speed and direction, and we can kind of get a sense of where it's going.
Exactly. And just like a rocket, where you got to factor in things like gravity in the quantum world, we got to consider the effect of those constant measurements, the core of the Zeno effect, remember?
So the Dunford-Segal approximation, it sets the stage for the Zeno effect to work its magic.
You got it. By breaking down our quantum system's evolution into these bite-sized pieces, we can see how each part is affected by those carefully timed measurements.
And then, with that multi-product approach we talked about, we can fine-tune those measurements to minimize errors and get that super stable quantum state we're after. It's like fine-tuning a high-performance engine.
Perfect analogy. Ready to see how MOBIS brings all of this together in the multi-product Zeno effect?
Lay it on me.
So, MOBIS's multi-product Zeno effect combines multiple Zeno sequences, each with its own step size. Think of it like having a bunch of photographers all taking pictures of a hummingbird in flight, each with a different shutter speed.
Okay, I can see that. Some might capture the wings frozen, others a blur of motion.
Exactly. Each Zeno sequence in this approach captures the quantum system's evolution at a different pace. We're talking simultaneous observation from multiple angles. And that's the key to better stability. Mathematically, it looks like this. K plus 1, C, M, E, T, L.
Okay, that's a mouthful. But let's break it down. I see. M, that's our quantum measurement, right? And L, that's like the driving force behind how our system changes over time.
Spot on. L, often called the Hamiltonian or Lindbladian, it dictates how the quantum system would evolve naturally if we just left it alone.
We're applying that evolution for a time. But it's the end that's interesting. It's like we're chopping up that time pin in a very specific way.
Exactly. That's the heart of the multi-product approach. Dean means we're running K plus 1 different Zeno sequences at the same time, each with its own step size. That's in E. And, well, that just helps us keep track of all these sequences running at once.
So like our hummingbird photographers, each one's taking a burst of photos, but they're all using a different burst length.
Right. Just like combining those hummingbird pictures from different shutter speeds gives us a much clearer picture of its flight, the multi-product Zeno effect uses information from all those different measurement sequences, each capturing the system evolving at a different pace to get a much more stable and robust quantum state.
Okay, this is seriously cool. But before we move on, let's appreciate the ingenuity here for a second. We've got these precisely synchronized measurements all working together. But what about those coefficients in the equation? They're up to something, aren't they?
Those coefficients. They're the unsung heroes in all of this. They make sure the errors from those Zeno sequences, remember those are unavoidable, actually cancel each other out.
So it's like we're putting counterweights on a mobile to keep it perfectly balanced.
You got it. Each coefficient tweaks the contribution from its Zeno sequence so the errors don't pile up and throw the whole system off.
And that's what gives us that impressive convergence rate, the 1 in K plus 1 we talked about earlier.
Exactly. It means that each new Zeno sequence we add makes our quantum freeze exponentially stronger. It's like adding more threads to a tapestry, stronger and more resilient with every thread.
This is blowing my mind. We can achieve a level of quantum control we could only dream of before just by carefully orchestrating multiple measurement sequences. So how does all this mathematical magic actually play out in the real world? Where can we see the multi-product Zeno effect in action?
Excellent question. From making those quantum computers of the future more reliable to controlling the delicate states of light, the possibilities are as mind-blowing as the theory itself. But I think it's time for a quick pause to let our listeners digest all of this. We'll dive into those applications when we get back.
And we're back. Deep divers, our quantum journey continues. We've gone through the math behind the multi-product Zeno effect, but how does this actually work in the real world?
Well, let's talk about a major hurdle in building those quantum computers everyone's buzzing about, dynamical decoupling. Imagine you have a qubit, the basic unit of information in a quantum computer.
Like our quantum coin, right? Flipping between states?
Exactly. Now, picture this qubit surrounded by chaos, a bath of particles and fields messing with its delicate quantum state. It's like trying to keep a soap bubble perfectly still in the middle of a tornado.
Sounds disastrous. That would lead to decoherence, wouldn't it? That's the ultimate enemy of quantum computing, right?
Right on the money. Decoherence is a constant threat, but we've got to cup our sleeves, dynamical decoupling.
Okay, I'm all ears. How do we shield our poor qubit from this chaotic environment?
Imagine hitting our qubit with a rapid-fire sequence of precisely timed control pulses. Each pulse momentarily shields the qubit from that chaotic environment, giving it a tiny break from the chaos.
So we're creating a shield around our qubit, momentarily protecting it.
Good analogy. But here's where it gets really interesting. Using the multi-product Zeno effect, we can fine-tune the timing and strength of those pulses. We're not just shielding the qubit, we're actually manipulating how it interacts with its environment.
Wow. So it's less about brute force shielding and more about finesse, right? Like a surfer riding a wave instead of just hiding from it.
Exactly. And the multi-product Zeno effect gives us the mathematical tools to choreograph those control pulses with incredible precision.
So we're taking this really abstract mathematical concept and using it to solve a very real problem in building quantum computers. Pretty impressive. But I bet that's just one application. What else can we do with the multi-product Zeno effect?
Let's switch gears from qubits to something completely different, light. Specifically, a coding scheme called the bosonic cat code.
Cat code. Now that sounds mysterious, like Schrodinger's cat.
You got it. This coding scheme uses cat states, which are just like Schrodinger's cat existing in two states at once. Except instead of a cat, we're talking about the electromagnetic field inside a microwave cavity.
Okay, so instead of a coin flip, we have a light switch that's both on and off at the same time, and we can store information in that state.
Precisely. The tricky part is controlling and manipulating these cat qubits.
It's like herding quantum cats.
You said it. And one of the key things we need to do with these cat qubits is rotate them, change their orientation in this strange quantum space. It's called the X-gate.
So we're gently steering our blurry light switch qubit in a specific direction. I'm guessing it's not as easy as just turning a dial.
You're right. This is where the multi-product Zeno effect comes in again. By carefully choosing a specific kind of Hamiltonian, remember that's the operator that governs our system's evolution, we can nudge our cat state into the desired rotation.
So we're using the Hamiltonian to gently push our cat qubit in the right direction.
Exactly. And by using a multi-product Zeno sequence with this carefully chosen Hamiltonian, we can make super accurate rotations. That's essential for building reliable quantum computers that use these cat qubits.
It's amazing how something as simple as observation can be such a powerful tool for manipulating the quantum world.
It really shows you the power of mathematics, doesn't it? The multi-product Zeno effect is a great example of how abstract theory can have a huge impact on real-world technology, and we're only just getting started.
I'm blown away. So as we wrap up our deep dive into the quantum realm, what's the key takeaway for our listeners?
The Quantum Zeno Effect is a weird but amazing glimpse into how the quantum world works. And the multi-product approach takes it even further, giving us incredibly precise control over these strange quantum systems. As we continue to explore the quantum realm, tools like this are going to be crucial.
A huge thanks to our expert for guiding us on this incredible journey. And for all you deep divers out there, keep those minds curious and remember sometimes the most amazing discoveries come from the most unexpected places. All right, buckle up, because today we are diving deep into some seriously hardcore math.
Absolutely.
We're talking about the multi-product Zeno effect.
Higher order convergence rates.
Oh, yeah.
This is for the math lovers out there.
This is going to be fun. So we're looking at this paper, multi-product Zeno effect with higher order convergence rates. And
those who are listening, I can already assume you're familiar with the Quantum Zeno Effect.
yeah, no kidding.
We're not going to do a basic rundown here. You know how observing a quantum system can slow down its evolution?
Yeah.
But this paper, this is where it gets really interesting because they're pushing the boundaries of how fast we can make that Zener effect converge.
Okay, so let's tie to error analysis because that's where this all starts, right?
Absolutely.
Page 2, they bring in this modified Chernoff lemma.
The core of it is this contraction C, right?
Mm.
Think of it as our quantum operation acting on a Banach space, our X.
Thought our quantum system.
Exactly. And this lemma, it's elegant, tells us how far off our practical Zeno effect is from the ideal continuous one. We're talking about applying C a certain number of times, n times.
And that difference, that error, they've got it captured in that integral equation, which, I'll be honest, looks a little intimidating at first glance.
It's dense, no doubt. But that integral form, that's the key. It lets us break down the error, see how each piece changes as we tweak it and how many times we apply our operation.
So it's like we're figuring out how to minimize the error by understanding its DNA.
Exactly.
Okay, so we've got our error analyzing lemma, and then they hit us with this modified Dunford-Segal approximation.
Right, because remember, we're always comparing, right, the perfect continuous Zeno evolution versus the one we actually do, step by step.
Right, like the difference between a smooth curve and a bunch of dots trying to approximate it.
Perfect analogy, and that's what Dunford-Segal quantifies, that difference. This paper, though, they tweak it, make it just right for the Zeno context.
Very cool. So now we've got these two powerful tools. What do they do with them?
Page 5. Things get really interesting. They derive a second-order expansion, specifically for the projective Zeno effect.
Because now we're going deeper than just the one error terms.
Right.
We're digging into that 1 and 2 level.
You got it. And they show something really cool. Under the right conditions, this expansion, we can keep taking it further. 1n3, 1n4, you name it.
Okay, so we're talking about the potential for much faster convergence here.
Exactly. And this is where the multi-product Zeno effect comes into play. But before we get ahead of ourselves, let's zoom in on this second-order expansion because it demonstrates something crucial. By choosing the right way to apply our C contractions, those 1 and 2 errors, they can vanish.
We can get rid of them completely.
Under the right conditions, yes. And that means a jump from 1 and 2 to 1 and 3 convergence, potentially even faster.
That's incredible. But we're talking about some pretty high-level math here. How do we even know these things hold true?
That's the beauty of it. They prove it every step of the way.
And that's where we need to dig into those inequalities they've derived.
Let's start with inequality 4.8, page 6. It gives us a limit, an upper bound, on how far off our Zeno approximation is from the real deal, the continuous evolution of an operator A under our Hamiltonian H.
Okay, so the smaller the right-hand side of that inequality, the better our Zeno approximation is.
Precisely. Now focus on that term with a 1 eternova. That's our dominant error, one of those higher order terms we were talking about.
And we can actually manipulate that, make it smaller by choosing our Zeno sequence carefully.
Exactly. And they don't stop there. Inequality 4.9, they generalize it. Now, it's not just one operator A, but a whole product of them. This is huge. It means we can apply this to a much wider range of operations in the quantum world.
This is amazing. They're building this whole framework, analyzing the error, finding ways to control it, and now making it applicable to more and more scenarios.
And it's all built on solid mathematical ground.
This is really groundbreaking stuff, but I feel like we're just getting started.
Oh, we're just scratching the surface here. We haven't even gotten to the real meat of the multi-product approach.
All right, well, cliffhanger.
Yeah.
We'll have to save that for part 2.
Get ready. It's going to be a wild ride.
I can't wait.
All right, so we're back.
And ready to dive into the multi-product approach.
This is where it gets really exciting.
No more teasing. Let's get into it.
Okay, so page 7.
Hit me with it.
We've got these higher order expansions.
You're right. We were talking about those.
And the idea here, it's ingenious.
Lay it on me.
Instead of one Zeno sequence, right, with its limitations, what if we use multiple?
Multiple.
Each one's running at a different, let's say, frequency.
Okay, I'm listening, but how do you even combine those?
That's the beauty of this. They figured out a way.
Yeah.
You choose those frequencies carefully.
Okay.
And the way you mix them together.
Like a recipe.
Exactly. You can actually make those lower order errors.
The ones that were holding us back.
Gone. They cancel each other out.
You're kidding.
It's like noise-canceling headphones, but for errors.
Whoa. That's wild.
We're talking about pushing that convergence rate way up.
Wow. To that 1 NK plus 1 they've got there.
Precisely. Each sequence on its own, it's limited. But together, boom, error gone.
So what's the it can't be that easy?
Well, there are some conditions.
Okay, really quick.
Page 8, they talk about periodic eigenvalues.
For the generalized multi-product Zeno effect.
Exactly. Those eigenvalues gotta have a certain rhythm.
So everything syncs up.
Exactly. It's all gotta be in harmony.
Okay, so some specific conditions have to be met.
But the point is, it expands what we can do with the Zeno effect massively.
It's like we've been driving this old clunker and now we've got a sports car.
A very precise, mathematically tuned sports car.
All right, enough with the abstract. Give me some applications.
Page 9, they talk about dynamical decoupling.
Decoupling, right. Isolating a system from noise.
Imagine the most fragile system.
Like a house of cards in a hurricane.
And we're building a shield around it with this multi-product Zeno effect.
Using measurements to silence the noise.
Exactly.
That's incredible. What else could we do?
Bosonic cat code.
Now you're speaking my language. For quantum computers.
You know how finicky those qubits are?
It's like they're allergic to existing.
This bosonic cat code, it's a way to protect them.
Make them more robust.
And guess what?
Multi-product Zeno effect to the rescue.
You got it. It helps us implement a key operation.
The X-gate.
With way higher fidelity than before.
So more reliable quantum computers because of this math.
It's all connected.
This is blowing my mind. We're not just talking theory anymore.
It's getting real.
Real exciting. But we're just scratching the surface, right?
Oh, absolutely. There's so much more to explore.
Well, we better get to it. What's next?
Hold on tight, because we're about to dive into a whole new world of possibilities.
Well, we're back.
And ready to explore the vast implications of this multi-product Zeno effect.
Because this isn't just about making things a little bit better. This is a whole new way of thinking about controlling quantum systems.
Absolutely. We've talked about specific applications.
Right, dynamical decoupling, quantum error correction.
But it goes way beyond that.
Okay, so what's the big picture here?
Think about quantum simulation.
All right, walk me through it.
You want to study some complex quantum system.
Like a new material or something.
Exactly, or even something like a black hole.
Whoa, okay, now we're talking.
Simulating those classically, it's a nightmare.
Our poor computers just can't handle it.
But quantum simulation, that's the key.
Using one quantum system to understand another.
You got it. It's like building a quantum scale model.
So we're letting the quantum world do the heavy lifting.
Exactly. And the multi-product Zeno effect gives us this incredibly precise way to control those simulations.
So we can really fine-tune those interactions, see what's happening.
It's like having the ultimate quantum microscope.
That's incredible. We're not just building better computers, we're using them to unlock the secrets of the universe.
And it's not just the big stuff either.
Ooh.
Think about metrology.
Metrology, measurements.
And the most precise measurements.
Atomic clocks, things like that.
Exactly. They all rely on quantum phenomena.
Which are super sensitive, I'm guessing.
And that's where the Zeno effect comes in.
To make those measurements even more accurate.
Precisely. By suppressing noise, improving stability.
So we're talking about better GPS, more sensitive instruments, all because we can control how often we look at something.
It's a whole new way of thinking about measurement.
It really is amazing how this one concept can have such a huge impact.
It shows how interconnected everything is.
One discovery leads to another, and who knows where it will end.
Exactly, and that's what's so exciting about this field.
So where do we go from here? What's next for the multi-product Zeno effect?
That's the million-dollar question.
Any guesses?
Well, we've got this amazing tool now. We need to experiment with it.
Try different combinations, see what works best.
Exactly. Find the perfect recipe for each application.
And maybe even push the boundaries of the math itself.
Absolutely. Can we relax some of those assumptions we talked about? Make it even more versatile.
It sounds like we're just getting started.
Oh, this is just the beginning.
Well, on that note, I think we've reached the end of our deep dive into the incredible world of the multi-product Zeno effect.
It's been a wild ride.
A huge thank you to our expert for guiding us through this mathematical jungle.
My pleasure.
And to our listeners, we hope you've enjoyed this journey into the heart of quantum control. And who knows, maybe this will inspire some of you to make the next big breakthrough.
The future is quantum.
Until next time, keep exploring.